Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to develop a concept in, of course, general mathematics and sciences, which is going to pertain to the concept of polar coordinates. Now, our last discussion that we had talked about the trigonometric, or the concept of trigonometry, we talked about the rectangular coordinate system. Now, these polar coordinates are going to assist us to describe functions, maybe in quantum chemistry, like the radio functions and the wave functions, and maybe other concepts that may be developed in quantum mechanics insofar as describing the position of a particle is concerned. So for that case, we're going to develop this using a two-dimensional space for the relationship that exists between the x and y axis and the angle, the extent of the angle that we had described when we were talking about trigonometry. So for that case, thank you and welcome. So as I've said, we talked about the rectangular coordinate system. We have got topic of discussion for today. So basically we're going to develop this one in two sets. The first one we're going to discuss on how we can be able to identify a particle that is moving in two-dimensional space, and that is going to give us a clue on how we can be able to describe it in terms of angles and the distances that I've talked about, that we had seen the relationship of trigonometric functions or the concept of trigonometry. So I'm going to draw this. It's a rectangular coordinates system which consists of the x and y axis, that's the horizontal and the vertical axis, and the point of origin at this point, we give it a notation for O. So suppose we have an array that runs from this point of origin to that point, and then that ray can be described using the x and y coordinates. So at this point, if it is point B, and I can be able to give it a notation of x, y. So therefore, this OP forms an array that of course intersects with OX at this. Let me assume that this is x, so this is a horizontal coordinate, probably the horizontal part of that rectangular coordinate, and it extends at an angle. Let me give it angle theta at that point. So I can be able to describe the distance between or the extent in the y direction by using just the term y, I mean the letter y, and let me give this distance r, and we're going to see the reason as to why we're just giving that. So let me just assume that this particular point is moving in a circular direction or moving at a constant direction from the point of origin, which is O, and I'm going to just have this distance shown in this particular direction. Let me just give this distance y, and then this is r, and the distance x. So basically I'm trying to just cut out this part of a right triangle that is going to be formed between the point O and this particular point. Let me call it R, and this R is different from the, okay, let me extend this one. This R is different from this particular circumference that is being prescribed by the motion of this particle along this circular motion, circular path, from a constant distance, which is from the point of origin. Now for any particle that moves around O at a constant distance, as I've said, it executes what we call a circle, which I've illustrated on the board. So in this case, this figure that is formed, if it executes a motion with a constant distance from point O, then it forms what we call a circle. And we have a relationship in this right triangle that we have described in our introduction, or maybe the concept of trigonometry, in that we have I can use this acronym to try and remind us ratios for those trigonometric functions, that is for the sine, the cosine, and the tan of theta. So therefore, we can be able to write to describe the distance x, or the cosine of theta, as x over r. The cosine of theta is equals adjacent over the hypotenuse, adjacent over the hypotenuse there, so therefore x over r. And number 2, I can be able to describe the sine of theta, which is opposite over the hypotenuse. Opposite is the distance between O and this point, which basically is the distance between point, this is r, and p, which has been given as y. So therefore I can write the sine of theta as opposite, which is y, over hypotenuse, which is r. So these two trigonometric relationships, which I can give as 1 and 2, can be rewritten as x for the first one is equals r, the cosine of theta, and then for the second one I can write y is equals r, the sine of theta. So given that, therefore, I can just do a rearrangement for that, or maybe give a relationship for that and try to see what. So from the Pythagoras theorem, we know that r squared can be given as x squared plus y squared. So this is a relationship that is given from Pythagoras theorem. So therefore, using these two relationships that I've written for those, I can be able to do a substitution for x and y, and therefore have the equation written as for x, for x, and then I'm going to have r squared is equals r, the cosine of x, but if we square this one, will give us r squared cosine squared plus y, r squared sine squared. Therefore, this one can still be just one extension to this point. This one can be rewritten, this second at the right part of the equation, which is this one, can be written as r squared into cosine squared theta plus the sine squared theta. Now the one in the brackets is referred to as an identity trigonometric ratio, as an identity ratio. So therefore it's going to just give us 1. The equation is going to be 1 is equals to the cosine squared, the cosine of theta squared plus the sine of theta squared. So I just do a substitution for that. So therefore this equation will give me the value of x squared plus y squared, representing r squared is equivalent to r squared. So therefore I'll just do away with this, just do a rearrangement. So therefore we write it as r squared is equals x squared plus y squared. Now that we have done a substitution for r at this point, and just to simplify this one out, we found that it's equivalent to this equation, or this part of an expression, and we have identified this one as an identity. So therefore it's going to give us a final equation of that kind. And in this case, we can describe the position of maybe a particle that is moving in a circular motion for this P that I've talked about, using the Cartesian coordinates as I've illustrated for x and y, as polar coordinates, maybe using that specific angle theta that we have been given in that case. So we are going to achieve this by just writing, if I can say that the point P a coordinate for the point P can be given as x, y, and we have just given a relationship between that angle and the x and the y. Therefore, I can be able to write that position of that particle. I hope we can be able to remember. I've done away with the figure that I was using to illustrate, but we can be able to remember since I've just given the equivalent for that. So we can be able to write it as P, of course, R theta. And of course, from this we can be able to give P, the point P, the position of the particle P as x R, the cosine of theta, and then for the R, the sine of theta. So therefore, trying to describe this in terms of angles, the angle that we have seen, this is going to give us what we call the polar coordinates. Now, in three-dimensional space for objects which are moving, of course, like the subatomic particles, this concept is going to be very important because we're going to describe this. As I said, this is the first part of the description. Of course, I've just stressed much of on the rectangular coordinates, but that is going to give us a prerequisite of trying to discover on how we can be able to represent the position of a particle in three-dimensional space. And that is going to assist us in trying to interpret some of the quantum numbers that we talk about in radio wave function and angular wave functions in quantum mechanics. So for this case, of course, remember where we have come from the Pythagoras theorem, trying to give the relationship of the trigonometric functions for x and y coordinates, and trying to figure out how we can be able to represent that one in form of an angle. And therefore, we try to develop the concept of a polar coordinate from that rectangular coordinate system that I've illustrated. So I hope that this is going to assist us. Of course, this part one of our discussion for this particular case of our coordinates. I hope it's going to assist us to try and understand the skills which are going to come further from this particular concept. So that is it for today. Bye guys. God bless.